It's my pleasure to present Transductive few-shot learning with prototype-based neighbor propagation by Iterative graph refinement. I'm Hao Zhu. This work is done with my PhD advisor Peter Cornelius. Our presentation focuses on the following problems. What are the issues with prototypes and graph-based transductive few-shot learning, and how to avoid the above pitfalls? Let's recall some details of prototype and graph-based methods. For prototype-based method, they usually use nearest neighbor classifier, which is based on the assumption that there exists an embedding where points cluster around a single prototype representation for each class. This figure shows a trial example that prototype-based methods are sensitive to the large within class variance and the low between class variance, and thus estimate prototypes inaccurately. For graph-based methods, they depend on the graph construction, which is commonly based on a specific kernel function determining the final result. If some nodes are wrongly and permanently linked, these connections will affect the propagation step. So, how can we avoid above pitfalls of transductive few-shot learning by unifying prototypes and graph-based method into a framework? In our paper, we propose prototype-based neighbor propagation. Our method can work with a generic feature embedding named on the base classes. This figure shows how to alternatively optimize a partial assignment between prototypes and the query set, and enable probability prediction by prototype-based neighbor propagation. Algorithm 1 summarizes our standard prototype-based neighbor propagation briefly. Specifically, 4 steps are included. In estimating assignment, we optimize a partial assignment between prototypes and the query set by solving a kernel regression problem or optimal transport problem. In constructing graphs, we use a small number of prototypes to turn sample-to-sample affinity computations into much simpler sample-to-prototype affinity computations. In propagating neighbor, we present how to learn a linear projection for improvement by limiting overfitting during propagation. In updating prototypes, we use gradient descent and the exponential rounding average to update prototypes to avoid instability. We evaluate our method on 4 few-shot classification benchmarks: mini ImageNet, timed ImageNet, CUB, and CVPR, all often used in transductive and semi-supervised few-shot learning. We use the standard evaluation protocols. Our model outperforms state-of-the-art methods significantly, consistently providing improvements across different settings, datasets, and training models. We also conduct ablation experiments on 4 different points: uniform class prime comparisons with the classical neighbor propagation, data augmentation for inference, and evaluations on class unbalanced setting. Thank you. Our code has been released in the following URL.